Yeah.
Yeah, go
So welcome everyone to this Soft Talk seminar. Today, I have the pleasure to have Amir Ghalamzan from University of Surrey. He was actually my classmate in my master time. Amir did his PhD at Polimi in Italy on using visions for robotics. And later he took positions at the University of Birmingham and Lincoln. He has several works on robotics for uh, uh, medical devices, for example, for detection of the breast cancer and teleoperations. And recently he has beautiful works on using robotics for agriculture. So Amir, thank you so much for joining today. So the floor is yours and we're looking forward to your talk.
Thank you. Hello, everybody. Good afternoon. I'm very pleased to be here and have this opportunity to present some of the works that we have been doing during the last few years. Thanks, Ahmad, for the introduction and also for the invitation. So today I'm going to talk about soft tactile sensing that we have been developing and robotic technology for picking soft fruits. And this is part of mostly have been placed in University of Lincoln, where I'm now based in University of Surrey. So strawberry picking is quite interesting and challenging problem. The challenges are multifaceted. The strawberries are soft and delicate, so the robot that we are developing should be quite precise, accurate, and also doesn't damage the fleshy part of the fruit. And the speed, and also the speed is another factor that we need to have it with the robot. So very accurate and precise movements with really fast, let's say, and fast processing. It has multiple aspects of the, let's say, complexities, which makes a really good and rich problem definition from different aspects for research. It has difficulty in perception. When I say difficulty in perception, we are looking at the strawberry images, and then we want to detect and segment the strawberries, localize the strawberries so that the robot understands where is the strawberry to go and pick it. In most of the cases, as you see here, and you see in the future, in the next slide, some of the berries are occluded by another one. So occlusion is really big problem that we need to think about it. And then the scheduling of the picking is also coming to the play, because if you pick one of the strawberries, it may make the next picking easier in terms of the, let's say, physical interaction, and also in terms of the perception. Motion planning and motion control are also really, really challenging, because we have lots of environmental, let's say, disturbances and changes. For example, lighting can vary from time to time, and that impacts your detection, segmentation, and also localization. Moreover, you may have wind in your farm, which makes your settings and all the, let's say, environment quite dynamic, where you need to sense and react in a quite quick way. So to give you a gist of what is the complexity of the problem, I would like to show you this this image, where you see lots of strawberries. Many of them are ripe, but they are quite entangled and quite, like, some of them partially occluded by others. The idea is that the strawberries are grown in cluster. Still, the 2D cluster or clutter manipulation is a kind of hot topic in robotic manipulation, where we are talking about 3D cluster manipulation, in which all this, let's say, strawberries are interconnected, and moving one of them can have some impact on the movements of the other strawberries. So this makes the perception and also the manipulation quite challenging. For that, we need to think about the active perception and interactive perception. Where with active perception, I mean that the robot needs to change the camera position to get new information, which results in non-occluded strawberries in some views. The interactive perception is when the robot interacts with the cluster, change the configuration of the cluster, and then collect some sensory information. It can be visual sensory information, or it can be tactile sensory information. So I would say that the tactile sensing would be under the interactive perception. So in my group, we started to look at the problem and then saw where we need to just develop some, let's say, knowledge and also some technology elements. And one of them was to just deal with the perception problem. As you see here, we have the simulation. We are benefiting a lot from the simulation, where the robot here is the frontal arm and is looking, there is a camera on the wrist, looking at just two berries, one ripe and one unripe, and goes around this two strawberry cluster, and look at the strawberries and try to detect segment from different angles. And then what we want to do, we want to make the robot intelligent enough by looking at an image. The robot can compute what would be the best pose for the camera, which gives the best detection segmentation performance for the strawberries in cluster. The other elements of the perception is the interactions that we are working on. So we are working to simulate the tactile sensor in the simulation and better understand how the robot can interact with the cluster, not just two strawberries cluster, but multiple strawberries cluster to reach a target berry to pick it quite successfully and effectively. So by introducing the problem, I would like to just jump into the work that we are doing on the acoustic tactile soft tactile sensor, which we call it AST skin, and why we came up with this, let's say, idea that we need to build our own tactile sensing, and what are the features of this tactile sensing and how that compares to the off-the-shelf tactile sensor that we used for a long time. Just to give you an example of some of the features shared across tactile sensor that we've seen, this is a gel site. We got one of them or two of them. We got a few of Zella sensor. So to give you an example of the limitations that off-the-shelf sensors bring, I would say that in some cases, we need to attach the tactile sensor to different shapes and geometry. The off-the-shelf sensors are coming in a solid box, and you cannot adjust it for your specific applications. So this is the first limitation. The second limitation, in some cases, the tactile sensors are quite bulky. For example, in a strawberry picking, we want to have the sensor which can penetrate among, let's say, strawberries and push them away, as you see in some of the demos that we built for, or we made for our strawberry picking, which this type of sensor doesn't permit such kind of limited space. So the gel side is a few centimeters by few centimeters. That means that you cannot do any, let's say, limited space manipulation. And then in some other cases, for example, I have been working on nuclear sort and segregation, or in space applications, you have a high contamination, and contamination means that electronics cannot last for a long time. So what you need is to just isolate electronics from your sensor and make your sensor, let's say, sensitive part of your sensor non-electronic, and then bring electronics in some safe, let's say, cases that contamination doesn't impact or doesn't destroy the electronics. In most of the tactile sensor, you can see that they have integrated electronics, which is another shortcoming that we observed. Then making the tactile sensor small is another factor, and the cost is the really big factor. For example, we are talking about gel side, which can cost around 3K, and each Zella sensor, which is a simple sensor, can cost around like 1,000 pounds. I see a bit of echo. If there is any mic or question, please let me know. All right. So some of the background work in acoustic tactile sensing or acoustic sensing, the group in Germany, Oliver Brook, TU Berlin, they have been working on this anthropomorphic hand for a while, and they come up with this idea that we can add the microphone and speaker to the sensor, and then what we could do, we can sense the, let's say, contact location and also some forces. So this is tactile sensor in definition. The idea was really interesting, as you see in the graph in the middle of the slide on top. The blue line is the played sound, and the orange line is, or orange curve is the recorded sound, where you see that just transmitting the sound within the chambers of this pneumatic fingers has some sound modulation. And this sound modulation can be used as a good feature to, let's say, to infer the contact properties, which includes the contact location and contact forces. In the graph below, you see that with different contacts at the tip, middle, and no contact, the magnitude or the amplitude of the sound is, the peak of the amplitude of the sound is shifted. So there is a good indication that you can use the sound as a medium to capture some tactile features and translate it into some tactile information. So the problem we had with that one, they almost claimed everything, but the problem is that they don't say that we built a tactile sensor. They add the tactile sensing capability to their fingers. And that is not what we were looking at. And we wanted to have a tactile sensor, which is plug and play, standalone, and you can just adjust it for your application, attach it to your soft robot, or you can just do it or attach it to any parts which are supposed to capture some tactile information. In our case, we started from the very basic and simple idea. We have a silicon, let's say, membrane in a case, and there is an acoustic channel which allows the speaker and microphone in two ends to send and receive some specific frequencies that we define. Then we have also the frameless tactile sensor to show that the sensor that we are proposing can be also used in a frameless and can be adapted to different sensing surfaces. To test, so there are lots of variables and lots of parameters to be studied. We just took the very early steps in order to shed the lights on this domain. So one of the questions we had was that is the geometry of the channels or acoustic channels are important to the capability of this sensor to capture tactile information or not. So we have been tested a few different configurations in which you see the cylindrical channels and also conical channels in different configuration, single channel, double channels, and with different configurations of a speaker microphones. And we wanted to just understand if a simple channel is enough for what we want, or we need to look at more complex channel, let's say, configurations. Either it is the channel cross area section, or it is like the configuration of different channels. And we wanted to also see if the configurations of the microphone and speaker impacts the performance of the sensor as well. So we have been, we just developed that sensor. As you see, this is the frameless sensor. And the pipeline of the sensor that you've seen is that we start from the reference acoustic signal, which is emitted by the speaker, goes through a cylindrical channel, U-shaped cylindrical channel in the frameless sensor, and it is received by the microphone, where the deformation on the surface of the sensor modulates the acoustic channel, acoustic signal. And then what we do, we pass it through some FFT operator, and then we use some, we tested several different machine learning models in order to understand how the modulation of the different frequencies can be correlated to the contact location and contact forces. So at the end of the day, once we build this, let's say, model, we can just test the sensor by collecting the data, collecting the, let's say, the received amplitude of the sound, and then predict or estimate the contact location and contact forces. Now, let's move on. So what we wanted to experiment, we wanted to explore different designs in this specific work, and we wanted to test it in a series of real robot applications. So it wasn't just building a tactile sensor and say that, look, our tactile sensor is really good, it is cool and it works. We wanted to use it in a specific application, which is pick and place. And we have tested different acoustic channel configuration. The features that we have, let's say, we have explored in this work was contact location, contact forces, and also real-world robot application. And also we tested the robustness of the sensor against ambient noise, which is not very well described in the original work by that German group. Okay, so we have this very simple case, and then for this simple case and the dual channel that you see here, for cylindrical channel and dual channel cylindrical conical with one mic and one speaker, we realized we get the best performance out of all 8 different configurations of the sensor for framed tactile sensor. The performance is 93% of force prediction are correctly or accurately predicted within the tolerance of 1.5 Newton tolerance for the range of forces from 0 to 30 Newtons. And the location estimation or the localization is 96% accurate. Our observation indicates that multiple channels with different, let's say, geometry outperforms the other configuration, and single speaker can serve multiple channel. The only difference, the only thing that we need to think when we are using single speaker is that the speaker can generate different frequency for different channels, and microphones should be separated so that they receive the corresponding, let's say, amplitude from different channels. So there are lots of questions that we are yet to explore in the future works, but we have done some of the analysis to understand what would be the best configuration for the speakers and also microphones. Then we moved on and we tested the sensor without any frames. So we attached it to this, let's say, curved finger. And we've done this very same, let's say, pipeline of collecting the data, calibrating the sensor, and then building the model which can help us or can give us the inference of the tactile force and also the contacts. And what we observed is that, interestingly, we just calibrated for 3 points, and everything is similar. Interestingly, you see that for the curved performance with the same number of contacts and the same calibration process, although the performance in the force prediction drops from 83% to 70%, from 93% to 89% for 1.5 Newton tolerance, it is quite good for location estimation. In location estimation with the framed tactile sensor or AST, we had 96% accuracy, while we have 99% here. So there are lots of factors that we need to yet explore, but that is interesting to see that with the curved, let's say, or with the curved finger, we have still a good and decent performance of the tactile feature prediction. Then we moved on and we tested the tactile sensor with for some pick and place tasks. This is the Franca. This is SMC gripper. Usually the grippers which comes with Franca, they don't permit the force control. So we had to use this bulky gripper that allows the force control in real time. And we have been using the object sets YCB, which is the quite well-known object sets in robotic manipulation community. And we tested per each object sets the pick and place task with set grip force of 2, 10, and 20 newtons, while where we repeat each pick and place task with the set grip force five times. So this is an example of picking the strawberry, which is a dummy strawberry, plastic strawberry. And this is the grip force that you see in real time, which is used to control the grip force of the SMC gripper. Oh, it doesn't show. Okay. Yeah, the process was quite slow. You see, it is quite nice. We can see really nice grip force control with the tactile sensor. The process was quite difficult for us because integrating SMC with the Franco was quite difficult. But at the end of the day, you see that how good the sensor can be used for grip force control and dropping the object. Well, one of the limitations that I see, and it is quite important to address it, is that when we when the robot drops the object, the value of the force, which is estimated by the tactile sensor, doesn't immediately go to zero or drops to zero. It takes like a second to converge to the zero, which is quite relevant to the nature of the deformable silicon, which takes time to get back to the original, let's say, forms, and that results in some delay in sensing the force, which is zero, but it takes it a second to get back to zero. We have done some tests for also the ambient noise impact on the sensor, and I don't show it here, but this is the closed loop control without and with a white noise present during the pick and place task. And you see that in both cases, the robot is successfully and effectively completing the task for grip force control of 10 newtons. All right, so the next natural step for us was to move from one-dimensional sensor that we had to two-dimensional sensor. And this has been quite nice. So we started to think about just expanding the sensing area from just one really line to a kind of area in 2D. And this is what we designed. So instead of having a U shape, we have an M shape acoustic channel in the silicon membrane. And then we wanted to make the sensor modular in the sense that we didn't want to build another sensor, which is 2D. So we made a 1D sensor, which is what you see here. And then we built two of them and attached it together orthogonally. The concept and pipeline are quite similar. So we have the microphone, a speaker emitting the acoustic sound, and microphone is receiving that, FFT, and then regression model. And what we are looking to estimate is contact force, 2D contact location. And in addition to this, we wanted to also see if we can get contact geometry estimation as well. So as you see here, this is the 1D on top, the image on the slides, on the top of the slides. And in the middle, you see the drawings of the 2D. So the 1D is the 1D sensor is first fabricated, and then we fabricate two of them and attach them together, where the M acoustic channels are orthogonal. The sensing area are 25 by 25 millimeter. In this case, as you see here, we wanted to take a step towards the continuous tactile sensor. So in most of the tactile sensors, which are not camera-based, for example, Zella has 4x4 matrix of sensing. It means that it gives discrete sensing points. But here we calibrated the sensor with 3x3 points, which is 9 points. And then we tested the contact location and contact forces for non-calibrated points as well with the 3 millimeters resolution. So that is a step towards the continuous tactile sensor with the same concept. And we have used two sets of the mic and a speaker, where we can reduce the number to one speaker and two mics, where the speaker can generate and emit the sound with different frequencies into two senses. So after this, we also tested cylindrical to keep it as simple as possible, and we wanted to measure the contact location and to the contact force and also the contact geometry. Calibration process, very similar. So we have used a U-factory arm, and we have a load cell here. So for the calibration, we build a peg which has 5, 7, and 9 millimeter. And then we press and apply forces at different locations by this peg. And the idea is to build the data set and see how those data sets can be used to train the machine learning models. The idea is that for single layer sensor, load is applied so the depth is quite limited with one layer sensor. When we build the two layers, since the width of the sensor are greater, then we can apply higher forces because it can deform and it can penetrate more into in two layers cases. So prediction of the machine learning models. In most of the cases, we trained different regression models. The best performing regression models in our case are Gaussian process regression. And as you see here, if we use if we look at the force, peg diameter, and location X and Y for single layer, you have the force, which is almost similar to the mean of the error of the force is almost similar to the two layers. They're really good. So if we are looking at, let's say 10 newtons, so it is 0.06 newtons error in average. And then peg diameters with the one layer sensor, you see it is quite considerable, since we had a peg of 0.5 centimeter, and here you see that the peg diameter is 0.3. So there is a considerable error, but with the bilayer skin, you see that the error for the peg diameter and also for the location is much smaller than the one layer sensor. So this indicates that the idea that we build two layers and we attach them orthogonally is helping us or makes the richer, let's say, data to infer this information. So that gives us also an indication if we want to have more, let's say, features estimated out of the acoustic signal, we can either make the, let's say, the sensing or the sensor more complex, or we can make more rich frequencies that passes through the acoustic channel. So that is another future works that we need to explore. Okay, so I will try to be faster as we have some other important things to cover, but I guess the most relevant works that I wanted to cover was the tactile sensor. Now we move on to some other works. For example, this work, we use the tactile sensor to just handle strawberries, which is the very same concept, just application, just to show you that how that fundamental ideas can contribute to some application. And then what we need for a robotic system to deal with strawberry picking is the motion planning. And for motion planning, we are working on the learning from demonstrations where it makes the motion planning much easier. So one of the problem that we have with classical imitation learning is that they are working mostly on the trajectory level. So they look at the trajectory and they want to identify or capture some patterns in the trajectory level and benefit that and link it to some hand-designed feature or some features which comes out of the computer vision, let's say, a component, and then that helps the trajectory to adapt to new situation. What we wanted to do is that instead of having the trajectory level learning from demonstration, we were interested to have a model that look at the scene, like the strawberries in this case, where the robot is in home configuration, and then maps this, let's say, image to the motion that the robot needs to perform in order to reach the strawberries to pick the strawberry. So this was what we've done with Alessandra. The slides that we have been covering so far was the work that Vishnu did. I will introduce the team at the end, but this was an MSc student visiting us in 6 months, and she worked on this learning from demonstration. The idea is that Alessandra is just demonstrating how the robot can move from home configuration to reach different strawberries. Then we wanted to build this, let's say, the AI component that maps the images that the robot sees to the robot movements or the distribution of the trajectories of robot movements, and then use this in order to automate the process and command the robot the movements. So this is the, let's say, the demonstration that Alessandra is doing. Then the idea is that we have the images input to autoencoder. The encoder extracts low-dimensional feature vector, and then the low-dimensional feature vector passed through some multi-layer perceptron, where this multi-layer perceptron defines discrete weights of the robot movements, and those weights multiplied by this basis function that you see in the image generate a distribution of the trajectory. Okay. All right. So we have proposed with a few different complex architecture with multi-stage training to train first autoencoder and then multi-layer perceptron, and then freeze a multi-layer perceptron and train for the second time the encoder part of the autoencoder to make it task specific. And what you see is that at the end of the day, we get the forward ProMP, which is mapping the image into the distribution of the trajectory as the output. And when I say distribution of the trajectory, it means that for a given image, there is a kind of random variable that you can set, and that gives you samples. So you can sample from that random variable. And in the model, you can give this value of the random variable, and the model propagate this through the, let's say, the ProMP and generate a new, let's say, trajectory within that distributions. So that enables the robot to have multiple different approach phases or approach trajectory for single strawberry, which is what we need to deal with occlusion. Here is a more complete, let's say, framework that of the training. As I told, you have multi-layer perceptron frozen, and then you use the trajectory space loss in order to train the encoder to make it task specific. So here you see example of the robot reaching the same strawberry with different approach phases. I repeat this again so that this enables the robot to sample or select different trajectories based on the perception performance. Okay, that is good. I guess I'm on track. And the last work that I want to present is about, so far we had, let's say, the perception side, then we had the sensor part. Then after that, we have seen some work that we have done about for motion planning. And the last thing that we need to do is motion control. Once the robot has the good planning, now the robot needs to control the movements based on the sensor information that receives in order to ensure the effective completeness of the task. So for this, what we have done, this is a very, let's say, a mock experimental setup of pushing strawberries in the lab. And the problem is that when you push a strawberry and the robot is just programmed to push the strawberry, if it doesn't get any feedback of how the pushing is going, then the robot may lose the contact with the strawberry stem. And the idea is that can we use tactile sensor in order to control the movements and ensure that the robot effectively change the configuration of the strawberry cluster in order to reach a target strawberry. This is another tactile sensor. It is custom. We build it ourselves. It is camera-based, as you see. There is a deformable membrane. A camera is looking at the membrane, and we have the AI model that maps the images into some tactile information, which is location and also the value of the pressure. So the thing that we proposed has two parts. The first part is the forward model that we presented at another paper, which is not the focus of what I'm telling. And the idea is that if you have a system and you don't have a model, so when we are pushing a strawberry, there is no analytical model how the strawberry are going to behave. So in this case, controlling this kind of task becomes very complicated because as you don't have any model how to interact with the environment. So the idea is that if we can make a model, which we cannot do it in analytical way, but we can do it in a data-driven way, then that model can take the, let's say, the future robot actions and then can predict what would be the tactile frames prediction corresponding to the planned robot actions in the future. That is really nice because then you can just close the control loop and you benefit or just employ any conventional control theory to control any complex task like strawberry pushing or any other nonlinear unknown tasks. So the blue block that you see here is the forward model, tactile forward model. As part of this forward model, we need to have the future robot actions, the history of the robot actions, the history of the tactile readings, and then what it predicts is the future tactile readings. And we are going to use that in our controller. Then we have the orange block, which is called CLM, which is contact localization model. And this maps the images into the location of the stem, simply. So after the blue block, which is the tactile forward model, the information goes to the contact localization model. And now we have the contact localization model predicted if the robot takes action X, for example. Now, as we have this, then we can say, okay, if the robot is going to take action X, it results to the error or displacement of the stem by this far. So we define the error for the future, or we predict the error for future robot actions. And then instead of waiting for the error to happen, and then the controller acts to minimize the error, we look at the predicted error and we try to damp the error to to not happen at all in the reality. So we predict there should be an error or displacement of the stem, and then the robot contracts that kind of displacement and doesn't let the stem to move on the tactile finger at all. So that is in simple word what we have done here. I show you one example, unsuccessful open loop control. Then I show you closed loop control for linear push and for circular push. So the idea here was that we collect lots of pushes with the tactile sensor. We train the predictive model and also contact localization model, and we use the output of the predicted contact localization to close the control loop and move the end effector in order to avoid the slippage. So the idea is to keep the contact between the stem and the strawberry and the finger constant during the pushing actions. Here we show how two controllers are performing. On top, you see PD controller, where the contact localization is used to make a PD controller. And at the bottom, you saw the video of deep functional predictive control, which is our controller. In the graph, you see two lines. Red is the contact location of two cases. For our proposed controller, red, the PD controller, blue. And you see that the blue is changing a lot. And in some cases, this change results in failure and losing the contact between the strawberry stem and the finger. So more of this, circular push. You see how variable is the contact location for the case of PD controller. And what we have done, we trained the model with single stem push, but we tested the performance of the controller on a cluster pushing. And as you see, with the cluster pushing, the performance of the our proposed approach is still not, it is not constant, but it is really close to constant, but the PD controller is just non-linear and it is changing a lot. And this was the case of the linear push, and then we have the case of the non-linear push, circular push. Okay, so after this, I want to just show the strawberry picking robot that we developed and we tested at the test facility at University of Lincoln, like in 2 years ago. And then after that, we also tested at Dyson Farming. That shows that what we are doing is quite intended to be applied and to be like creating impact. And that is of our interest in most of the case. But you see that how solving a problem. So this is very small video. I can show you probably other videos, which is better than this. And by this, I want to conclude and thanks everybody. I would be happy to take questions. Before that, I want to say a word that all of the work or most of the work that you have seen are done by these people. Vishnu was the person leading the tactile sensor, the AST sensor development. Kianush and Vilo worked on the data-driven control, and Alessandro worked on the learning from illustrations. Thank you.
Thank you so much, Amir. It was an excellent talk. You close the loop through from the sensing, to the control and then through the applications. So now it's time to take questions from the audience, please.
There is already one question in the chat session.
Oh, I missed that. Just let me see. So yeah, Manmata, I just read out the questions. Thank you for your excellent presentation. I greatly appreciate the opportunity to learn about your impressive work. I have a few questions regarding the calibration and sensitivity of your sensor. Specifically, I would like to know how often is calibration required for the tactile sensor? Question 2, Is the sensitivity of the sensor dependent on the material properties or environmental conditions?
Thank you. Thanks, Ahmad. Yeah, so the calibration in all of the work that we have done, we did calibration once and we tested. So it wasn't let's say calibration. We had some, so the environmental factor definitely impact the calibration. For example, temperature impacts the calibration. But if we are going to use like the sensor to make it robust against environmental factors, definitely we need to test, we need to collect data in different environmental situation. And then by a rich data set, definitely calibration improves. And also by inputting the, let's say, inputting the environmental situation. For example, if you are calibrating the sensor in 20 degrees and then you have calibration in 30 degrees, then you need to have this information while you're using the sensor so that it gives the right, let's say, output for different environmental conditions. The material, yeah, definitely impacts the sensitivity. We have tested the concept with silicon. We tried some 3D printing to make the sensor more flexible, but it wasn't quite. It was we were not successful to get a 3D printing, let's say, durable. So it was breaking easily after a few, let's say, iteration. So there are things that we need to consider and study in the future, but material impacts the sensitivity of the sensor.
Okay. I
Yeah,
have a
thank you
question
very
also,
much. Yeah.
regarding the application, of the strawberry picking. Is it the sensing needed for touching the strawberry itself or the stems, or what is,
Now the
the
idea is that okay, so I learned a lot about how human is picking strawberries, and I work with a supervisor from the funding agency that she was the one who found one type of a strawberry. So to that extent, and I know that there are 300 different varieties of strawberries. So she was finding one of them. And she told that even human, when they touch the strawberry, and if you go and buy the strawberries from the shelf in the supermarket, you see that the strawberries start bruising from specific point. So these bruising points are exactly the points that human touched it. Even the simple touch initiate the bruising. So the idea is to minimize the touch on the fleshy part of the fruit and just go for the stem and pick by cutting the stem.
Now we have a question from Ali, please.
Yes, thank you. Thank you for the very nice presentation. Two things actually comes to my mind. One is that over some time ago, I have also seen similar concept using the light through a channel, and basically you are have a light transmitter, and then you have a receiver, and based on the channel deformation, you can detect. So have you done like that comparison, or thought that, okay, what are the similarities between the two? And the second thing, is there a particular range of frequencies, or you have thought found maybe changing from one to another makes it more sensitive and so on?
Yeah, we have done quite extensive analysis on the frequency, which is available in the paper, and there are yet more to do in the analysis of the frequencies. They are really important. We okay in the when we were testing, it is fine if you. So, for example, if you have a white noise with some limited amplitude, the sensor is working fine. But during the development, Vishnu was working in a kind of garage in the farm, and there was a tractor where the tractor was operating. You couldn't hear each other. So that time was where the sensor couldn't work at all. And we realized, okay, there is a boundaries on when the sensor works. So the the kind of white noise is okay, but to some extent, if the magnitude of or amplitude of the white noise is so large that you can not even hear each other, definitely the sensor doesn't work. So the frequencies are important, and you can play with the frequencies, with the amplitude, because if you choose to have a large amplitude of the frequencies, then you hear a lots of noise of the sensor during the work. But if you use the smaller frequencies, probably it's better in terms of the, let's say, comfort for the people who are working there. The other elements that you ask is about light.
Parallels between the two.
Yeah, so I guess light is interesting. The way that we started to look into this problem is that, okay, any medium that captures the deformation is good. Light is good, but we had other let's say considerations as well. Cost was one of them, and the let's say simplicity was one of them. I know that people are using optical fiber for curvature estimation, which is absolutely fine, but there is a certain limitations to use optical fiber. I don't know, when you say light, you're talking about optical fiber or other type of the, let's say, transmission medium?
Optical fiber, what I have seen.
Okay,
Yeah.
okay. I guess there are limitations there, at least because we have the same sensor. We are submitting the paper for curvature estimation. So the frameless sensor, the variations of the frameless sensor that you've seen, we have tested for curvature, and it is quite precise. And in that, we realized that the optical fiber, they have limitations on the bending. So they can, that there is a limit on how much they can bend. So if you
Okay.
press the optical fiber probably too hard, you can break it easily.
Okay. Thank you. Thank you very much.
A pleasure.
So next question from Jonathan. Yeah.
Good morning. Congratulations. It was a very interesting talk.
Thank you.
And also the topic. I feel curious about one part of the design of the sensors. You told that you had a variety of 8 types of distribution of the 2 channels. And I would like to know, how did you choose one of these designs, or basically in which parameters you find that is the most effective one?
So for the acoustic channel shape, you mean? Yeah, I guess
Yeah.
it was, so we had a really difficult time to publish the paper because of the original paper. And the tools to do acoustic mechanical analysis or simulation, we couldn't find it. There are probably some available that we couldn't explore it. Probably the best way would be to simulate the settings and see what is the best configuration. We empirically just test the different settings, and we come up with some idea. Okay, this is the best performance. The another factor to choose the acoustic channel shape was the difficulty of fabrication, because we didn't do the 3D printing. We had some problem with the 3D printing. We tested non-solid 3D printing structure, which gives us better, let's say, deformation or variable stiffness property. But with the silicon and simple fabrication methods, the cylindrical shape is the best that you can do, because you can just put some solid, let's say, cylinders there and then remove it, and then you have the sensor ready. But for other types, you need to think about more complicated fabrication, which absolutely is a way to go. And if there are potentials, Vishnu finished his PhD, and I don't have yet another PhD or any resource to work on it at the moment.
Yeah, we have Samuel in the queue.
Yes. All right. Thank you, Amir, for your talk. In relation to the tactile sensor, you were testing for when it was deformed and found it had good touch location sensitivity. But when you actually showed the sensor on the robot, it still seemed quite flat. Did you do any testing with the sensor actually deformed on an end effector?
No, we didn't. But for the strawberry picking robot, eventually we need something which is not flat. So that's why we worked on non-flat and a sensor technology that can be adapted to different geometries. But that would be part of the future work, definitely.
Thanks.
Sarwana?
Yeah. So thanks for the talk. It was very interesting. I have two questions for the acoustic sensor. So when you're grasping a strawberry, you also showed that can measure the force, but what force? It's a normal force. It can also differentiate between the shear because you get some shear when you're grasping it. And another question followed up on the same is the friction. So could, like a texture, can the sensor able to detect the texture when you're touching or the friction itself while grasping it? So
Okay, thank you. Yeah. As I told, these are just initial step we took. Definitely the next step for us would be shear. We didn't test the shear. I can speculate that for the shear we need more complex structures that can let the deformation of the channels correlates with the shear. At the moment, the symmetric cylindrical shape probably doesn't have the capability of capturing that correlation. But with some other shape of the channels, definitely shear would be another interesting extension of the tactile sensor. About the texture, what we have, if you look at the off-the-shelf tactile sensor, most of them are pressure sensor, which are distributed, like giving you a set of normal readings, and that's all that you get. With the more advanced sensor, for example, Zella gives you 4 by 4, 16 cell of normal forces and shear forces. And when you're working with shear forces, they are crazy because in our mind, the shear is quite clear and clean. But when you look at them, it is quite confusing. And at the end of the day, you say, OK, I don't want to use shear. Let's just use the normal forces. But the texture that you referred, the texture is quite the feature which is available in camera-based tactile sensor. For example, if you look at the gel side, they are giving you a really nice high-resolution texture, but they cannot provide with normal forces, or they are not calibrated at least for normal forces and shear forces. So it depends on what you want to get. From one hand, you can have a really good sensors that can provide the texture, or on the other hand, you can get a magnetic-based tactile sensor, which gives you just normal and shear forces. And you should just set your, let's say, the selling point of your sensor. Definitely, you can think about some membranes which are sensitive enough to capture the texture, and then some channels which can capture this kind of features which are correlated to the, let's say, the amplitude changes. But I would say for most of the applications that we have, normal and shear forces are most relevant and more important.
great, thanks.
All right, I think we are reaching to the end of this session. Thank you so much, Amir, for joining us and sharing your results.
Thanks, Ahmad, for the invitation.
Back, with you and with your team in future. And thank you for everyone for joining and making this talk more interesting. Yeah, thank you so much.
Thank you, everybody. See you.
Bye.